Namaste, my friend, and welcome back to JEE Physics with Typical Monk. This is class 10, and today we step into fluids: water in a pipe, a coin sinking in a glass, a drop climbing a thin straw. Push a fluid anywhere, and it pushes back everywhere at once. Sarah once thought a floating ship was a small miracle of engineering, and in a sense it is, but it obeys the very same principle as the coin that sinks beside it. One idea, weight against the weight of the fluid it displaces, explains both. And here is why fluids reward G thinking especially well. Nearly every result here comes from balancing forces, the same calculus habit you have been building since class 1. Take a slow breath. Let us begin. So what will you carry home from today's class? First, pressure, Pascal's law, and the hydraulic lifted quietly powers. Second, buoyancy and Archimedes principle, how much weight a fluid truly takes off your hands. Third, the continuity equation and Bernoulli's theorem with their two-star applications, the Venturi meter and Torricelli's law. Fourth, viscosity and Stokes' law, terminal velocity, found by balancing three forces at once. And fifth, surface tension, excess pressure, and capillary rise, where a curved surface does surprisingly strong work. Ready? One idea at a time. Let us start where every fluid problem starts, with pressure. Pressure is simply force spread over area, measured in pascals, 1 Newton over 1 square meter. Small area, same force, huge pressure. That is why a needle pierces skin a flat thumb cannot. Now, Pascal's law, the generous idea. Squeeze an enclosed fluid anywhere, and that extra pressure reaches every point inside it equally, undiminished. This is exactly how a hydraulic lift raises a car with one hand. A small force on a small piston becomes a huge force on a big piston, because the pressure between them must match. And one trap worth naming now. Absolute pressure equals atmospheric pressure plus the fluid's own rho GH. Most students quietly forget the atmosphere and lose the mark. Look at this flowing pipe carefully, because it hides two ideas working together. First, continuity. Whatever volume of fluid enters a pipe each second must leave it each second, so area 1 times speed 1 equals area 2 times speed 2. Squeeze the pipe and the flow must speed up. Second, Bernoulli's theorem, which forces pressure and height into that same speed. Pressure plus half rho b squared plus rho GH stays constant all along one streamline. So watch the manometer columns in the diagram. Where the pipe narrows, speed rises, and pressure must fall to keep the total constant, exactly why the shorter column sits over the narrow throat. David once assumed a narrow pipe always means higher pressure, the way a queue would feel more crowded. It is the opposite. Narrower means faster, and faster means the pressure has to drop. Now, what can this one constant actually do for us? And just as important, where does it stop working? It derives Torricelli's law. A hole near the bottom of a tank lets fluid out at a speed of root 2 GH, as if it had simply fallen that height. It measures flow in a Venturi meter. The pressure drop between a wide section and a narrow section tells you exactly how fast the fluid is moving. It even explains dynamic lift. Shape a wing so air rushes faster over the top than underneath, and Bernoulli turns that speed gap into an upward push. But here is the honest limit. Bernoulli assumes the flow is steady, incompressible, and free of viscosity. Inside a thick, viscous, or turbulent stream, the constant quietly stops being constant. Lisa once applied it inside a narrow oil-filled tube and wondered why her answer drifted from the measured value. Viscosity was eating. The energy Bernoulli assumes never leaves. Time to solve a full G numerical together. Slowly, the monk's way. Sarah drops a small steel ball of radius 1 millimeter into a tank of oil and lets it fall until it reaches a steady terminal speed. The ball's density is 8,000 kilograms per cubic meter. The oil's density is 800. The oil's viscosity is 0.2 Pascal second, and gravity is 10 meters per second squared. Find the terminal velocity. Step 1. Write down what is given. Radius 1 millimeter, ball density 8,000, oil density 800, viscosity 0.2, gravity 10. At terminal speed, weight exactly balances buoyancy plus the viscous drag pulling upward. Step 2. The formula. Balancing those three forces on a sphere gives V equals 2r squared times the density difference times g all over 9 eta. This is the calculus of a force balance, not a formula to simply memorize. Step 3. The numerator. 2 times 1 millimeter squared times the density difference of 7,200 times 10 gives 0.144. Step 4. The denominator. 9 times 0.2 gives 1.8. Step 5. Divide. 0.144 over 1.8 gives 0.08 meters per second, which is 8 centimeters per second. Notice the method. Given, formula from the force balance, numerator, denominator, then divide. The same 4 moves solve every terminal velocity numerical G can ask. Now, 2 more ideas that ride on the surface and the weight of a fluid. Buoyant force is nothing but the weight of the fluid. A submerged object pushes out of the way. So apparent weight in a fluid is always less than the true weight, never more. John once assumed a solid block of steel could never float, and yet a steel ship does, simply because its hollow shape displaces enough water that the ship's overall density beats the water's. Now capillary rise. A thin tube dipped in a liquid pulls that liquid up to a height of 2t cos theta over a rho g. Make the tube narrower and the liquid climbs higher still. And one sharp G fact, a soap bubble has 2 surfaces facing the air, while a simple drop has only one, so a bubble's excess pressure is exactly double a drop's of the same radius. Now sit up straight. These 5 lines are what G actually asks, year after year. 1. Pressure plus half rho v squared plus rho gh stays constant along one single streamline. Never assume it links 2 completely separate flows. 2. Terminal velocity rises with the square of the radius. Double the radius and a terminal speed becomes 4 times as large. 3. Apparent weight in a fluid is always the actual weight minus the buoyant force, and it can never be written the other way round. 4. A bubble's excess pressure is double a drop's of the same radius, purely because a bubble carries 2 surfaces, not 1. 5. Always keep gauge pressure and absolute pressure apart. The atmosphere is the silent term most students forget to add back in. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. A block floats with 3/4 of its volume submerged in water. Reason. The density of the block is 3/4 the density of water. Think like SATA. Check each statement, then the connection. Floating means weight equals the buoyant force. So the block's density times its full volume must equal water's density times 3/4 of that volume, and that gives exactly the reason stated. Both true. Reason explains. Option A. Second one. Assertion. The excess pressure inside a smaller soap bubble is greater than inside a larger one. Reason. Surface tension pulls a curved liquid film inward from every direction. Both statements are true. But pause. Does the reason explain the assertion? Not quite. The real reason the smaller bubble wins is that excess pressure varies as 1 over the radius, not merely that surface tension pulls inward, which is true of every bubble regardless of size. Both true, but the reason does not explain the assertion. Option B. This is the trap that catches John every time. Third one. Assertion. A hydrometer sinks deeper in a liquid of higher density than in a lighter one. Reason. For a floating body, the buoyant force equals the weight of the liquid displaced. Check the reason first. That is simply Archimedes' principle. True. Now the assertion. A denser liquid needs less volume displaced to support the same weight, so the hydrometer actually sinks less, not deeper. The assertion is false. The reason is true. Option D. A quick match now. Say each formula aloud before I reveal it. Hydraulic lift Force 2 equals force 1 times area 2 over area 1. A small push, hugely multiplied. Continuity equation. Area 1 V1 equals area 2 V2. Mass simply cannot pile up inside the pipe. Terminal velocity 2r squared times the density difference times g all over 9 eta. Balance 3 forces and this falls out. And capillary rise 2d cos theta over r rho g. Surface tension lifting a liquid against its own weight. If all four came to you before the reveal, fluids are becoming yours. Here's a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. The excess pressure inside a soap bubble is 4T over R. Hold your verdict. Statement 2. Terminal velocity of a sphere in a viscous fluid is directly proportional to its radius. Think of the force balance before you answer. Statement 3. A liquid rises higher in a capillary tube of smaller radius. Picture the 2d cos theta over r rho g formula. So, how many are correct? Two statements, the first and the third. A bubble's two surfaces really do give it 4t over r, and a narrower tube really does pull the liquid higher. But the second one falls. Terminal velocity goes as the square of the radius, not the radius alone. Two correct, and the middle one is the trap. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. A heavier object always sinks, and a lighter one always floats. It feels so natural, surely weight alone decides. But here is the truth. Floating depends on density compared with the fluid, not weight alone. A massive steel ship floats because with the air inside its hollow hull, its overall density beats water's, while a small solid steel ball sinks at once. Myth 2. Gauge pressure and absolute pressure are simply the same thing, since both measure the same fluid. The truth, absolute pressure equals gauge pressure plus atmospheric pressure, and dropping that atmospheric term silently shifts every manometer and barometer answer. One myth, one full G question. Do not let it be the one that costs you. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. What is the gauge pressure 10 meters deep in water with density 1000 and gravity 10? Bro G Hake is 1 times 10 to the power 5 pascals. Question 2. A wooden block of density 600 floats in water. What fraction of it stays submerged? Density ratio gives 0.6 or 60%. Question 3. If the radius of a falling sphere doubles, its terminal velocity becomes how many times as large? Radius squared gives 4 times. Question 4. Excess pressure inside a bubble of radius 1 millimeter, surface tension 0.03 newtons per meter. 4T over R gives 120 pascals. And question 5. The thinker, speed of efflux from a hole 5 meters below the free surface with gravity 10, root 2 G gives 10 meters per second. If you caught that one, you have truly understood today's class. Let us gather the whole class in one slow breath. Pressure is force per area, and Pascal's law spreads any change in it equally through an enclosed fluid. Buoyancy is the weight of the fluid displaced. Apparent weight in a fluid is always less than the true weight. Continuity keeps area times speed constant, and Bernoulli keeps pressure plus half rho v squared plus rho g Hake constant along a streamline. Stokes' law balances weight against buoyancy and viscous drag, giving a terminal velocity that grows with the square of the radius. Surface tension curves a drop and drives capillary rise. The narrower the tube, the higher the climb. And next class, we turn to heat itself, thermal properties, calorimetry, and the kinetic theory of gases, where pressure finally meets moving molecules directly. Do not miss it. And so, my friend, we have crossed into the world of fluids. It may have looked like water and oil and soap bubbles. But understand this. The same weighing of forces you practice today on a falling ball or a rising drop is the very habit G rewards in every branch of physics. Sarah, David, Lisa, and John all found their footing here exactly where you are now. One careful force balance at a time. Be patient with yourself. Tonight, revise just the 4 core results once, slowly. Pascal's law, Bernoulli's constant, terminal velocity, and capillary rise. One idea at a time, you will crack JEE. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in the world of heat.